Welcome to the first part of the RSET training, Climate Change Monitoring and Impacts using Remote Sensing and Modeled Data. My name is Sean McCartney, and I am joined today by my colleague, Amita Mehta. This two-part introductory webinar series will provide an overview of NASA resources for monitoring climate change and its impacts. The two-part webinar series will define the terminology and the role of Earth observations in climate change assessment and provide an overview of NASA climate models suitable for emissions policy, impacts, risk, and resilience applications. After participating in this two-part training, attendees will be able to explain the difference between weather and climate, summarize the evidence and causes behind climate change, identify how Earth observations are used in climate change assessment, recognize the main components relevant to climate change decision-making, summarize different types of climate information across time scales, and discuss how models can be used for climate change adaptation planning. A prerequisite for the two-part training is RSET's Fundamentals of Remote Sensing Session 1. This Fundamentals course provides a general overview to remote sensing and its application to disasters, health and air quality, land, water resources, and wildfire management. Those who take the Fundamentals course will become familiar with satellite orbits, satellite types, resolutions, sensors, and processing levels. As already mentioned, this is a two-part training focusing on climate change monitoring and impacts using remote sensing and modeled data. Today, in Part 1, we will be covering climate change monitoring and impacts using remote sensing and modeled data. In Part 2, scheduled for next week on October 6th, we'll be covering climate change future scenarios, impact predictions, and adaptation. The second part will be led by colleagues from NASA's Goddard Institute for Space Studies. There will be one homework assignment for both parts of the training. Answers must be submitted via Google form, which can be accessed from the training page on the RSET website. Homework will be made available on October 6th with a due date of October 20th. A certificate of completion will be awarded to those who attend all live webinars and complete the homework assignment by the deadline of October 20th. You will receive a certificate approximately 2 months after the completion of the course from Marinas Martin. The outline for Part 1 of the training is as follows. I will briefly describe the RSET program. We will provide an overview of climate change, as well as the role of Earth observations in climate change assessment. We will then demonstrate how to monitor climate change impacts using NASA data. And finally, we will cover the main components relevant to climate change decision-making. RSET provides accessible, relevant, and cost-free training on remote sensing satellites, sensors, methods, tools, and applications. Trainings are offered online and in person for beginners and advanced practitioners alike. Though unfortunately, due to the COVID-19 pandemic, the program has suspended in-person training. Trainings cover a range of datasets, web portals, and analysis tools, and their application to air quality, agriculture, disasters, land, and water resources management. Trainings are freely available to anyone with an internet connection and conducted either live, instructor-led, or self-guided, such as the Fundamentals to Remote Sensing course mentioned in the previous slide. Since 2009, the program has reached over 50,000 participants from 170 countries. We've provided a link on the right of the slide to learn more about the program and hope you will sign up on our listserv to stay informed about future trainings. The following slides are intended to provide an overview of climate change. The terms weather and climate are sometimes confused, though they refer to events with broadly different spatial and temporal scales. There is an adage, weather tells you what to wear each day. Climate tells you what types of clothes to have in your closet. Similarly, the terms climate change and global warming are often used interchangeably but have distinct meanings. We will go into details for each of these terms over the following slides. Weather refers to atmospheric conditions that occur locally over short periods of time, from minutes to hours and days to weeks. Familiar examples include rain, snow, clouds, wind, or thunderstorms. Most weather happens in the part of Earth's atmosphere that is closest to the ground, called the troposphere. There are many different factors that can change the atmosphere in a certain area, such as air pressure, temperature, humidity, wind speed, and direction, and lots of other things. Together, they determine what the weather is like at a given time and location. Climate, on the other hand, refers to the long-term local, regional, or global average of temperature, humidity, and rainfall patterns over a period of time, often 30 or more years. When scientists talk about climate, they're looking at averages of precipitation, temperature, humidity, sunshine, wind velocity, phenomena such as fog, frost, and hailstorms, and other measures of the weather that occur over a long period in a particular place, again, typically 30 or more years. Climate can help us describe whether the summers are hot and humid and whether the winters are cold and snowy at a particular place. They can also tell us when we might expect the warmest day of the year or the coldest day of the year at that location. Across the planet, observers and automated stations measure weather conditions at thousands of locations every day of the year. Some observations are made hourly, others just once a day. Over time, these weather observations allow us to quantify long-term average conditions, which provide insight into an area's climate. In many locations around the world, systematic weather records have been kept for over a century. With these long-term records, we can detect patterns and trends. Just as we can describe regional climate, we can also describe the climate of the entire planet. Global climate is a description of the climate of a planet as a whole, with all of the regional differences averaged. Global warming is the monotonic, long-term heating of Earth's climate system observed since the pre-industrial period, which is between 1850 and 1900, due to human activities, primarily fossil fuel burning, which increases heat-trapping greenhouse gas levels in Earth's atmosphere. Worldwide, since 1880, the average surface temperature has risen by about 1 degree centigrade relative to the mid-20th century baseline, which is from 1951 to 1980. This is on top of an additional 0.15 degrees centigrade of warming from between 1750 and 1880. Average surface temperature is calculated by averaging the temperature at the surface of the sea and air temperature over land, derived from thousands of meteorological stations, buoys, ships, and satellites around the planet. Climate change is a long-term change in the average weather patterns that have come to define Earth's local, regional, and global climates. It encompasses global warming, but refers to the broader range of changes that are happening to our planet, including shrinking mountain glaciers, accelerating ice melt in Greenland, Antarctica, and the Arctic, rising sea levels, shifts in phenology, ocean acidification, coral bleaching, as well as extreme weather. The natural variability and the climate fluctuations of the climate system have always been part of Earth's history. The Earth has gone through warming and cooling phases in the past, long before humans were around. To understand climate change fully, the causes of climate change must first be identified. Natural processes can contribute to climate change, including internal variability, for example, cyclical ocean patterns like El Nino and La Nina, and external forcings, for example, volcanic activity, changes in the sun's energy output, as well as variations in Earth's orbit. These natural causes are still in play today, but their influence is too small or they occur too slowly to explain the rapid warming seen in recent decades. Changes observed in Earth's climate since the early 20th century are partly driven by human activities, particularly fossil fuel burning and deforestation, which increases heat-trapping greenhouse gas levels in Earth's atmosphere, raising Earth's average surface temperature. Carbon dioxide and other substances are referred to as climate forcers because they force or push the climate towards being warmer or cooler. They do this by affecting the flow of energy coming into and leaving the Earth's climate system. Many of these greenhouse gases occur naturally, but human activity is increasing the concentrations of some of them in the atmosphere, in particular, carbon dioxide, methane, nitrous oxide, and fluorinated gases. Carbon dioxide, produced by human activities, is the largest contributor to global warming. By 2020, its concentration in the atmosphere had risen to 48% above its pre-industrial level, which is before 1750. I will go into more detail on each of these greenhouse gases later in the presentation. This graph illustrates the change in global surface temperature from 1880 to 2020 relative to the 1951 to 1980 average temperatures. The years 2020 and 2016 are tied for the warmest on record throughout this 140-year period. As stated previously, global surface temperature is calculated by averaging the temperature at the surface of the sea and air temperature over land, derived from thousands of meteorological stations, buoys, ships, and in the past few decades, satellites orbiting our planet. Natural variability and climate fluctuations of the climate system have always been part of Earth's history. The Earth has gone through warming and cooling phases in the past, long before humans were ever around. In the last 650,000 years, there have been 7 cycles of glacial advance and retreat, with the abrupt end of the last ice age about 11,700 years ago, marking the beginning of the modern climate era and of human civilization. The last glacial maximum, roughly from 26,500 years ago to 20,000 years ago, was the most recent time during the last glacial period that ice sheets were at their greatest extent. Ice sheets covered much of North America, Northern Europe, and Asia, and profoundly affected Earth's climate by causing drought, desertification, and a large drop in sea levels. During this last glacial maximum, again, between 26,500 years ago to 20,000 years ago, much of the world was cold, dry, and inhospitable, with frequent storms and a dust-laden atmosphere. The dustiness of the atmosphere is a prominent feature in ice cores. Dust levels were as much as 20 to 25 times greater than they are today. The massive sheets of ice locked away water, lowering the sea level roughly 125 meters, or about 410 feet, lower than it is today, exposing continental shelves, joining land masses together, and creating extensive coastal plains. The current warming trend of the Earth's climate is of particular significance because it has been accelerated by human activity since the mid-20th century. Climate scientists separate factors that affect climate change into 3 categories: forcings, which I've briefly mentioned, feedbacks, as well as tipping points. Climate forcing refers to an energy imbalance caused by natural or man-made processes, and is the difference between the rate of energy received by absorption of solar radiation and the rate of energy emitted by the top of Earth's atmosphere, expressed in watts per square meter. Contributors to climate forcing are solar irradiance, greenhouse gas emissions, and aerosols, dust, and smoke. Solar radiation is the source of heat for planet Earth. Scientists also use evidence from proxy measurements, such as sunspot counts going back centuries, and ancient tree rings, to measure the amount of sun that reaches Earth's surface. The sun has an 11-year sunspot cycle, which causes about 0.1% of the variation in the sun's output. The solar cycle is incorporated into climate models, which will be covered in depth in part 2 of this training next week. Since the Industrial Revolution, concentrations of greenhouse gases such as carbon dioxide, methane, and nitrous oxide have risen in the atmosphere. Burning fossil fuels such as coal, oil, and gas has increased the concentration of atmospheric carbon dioxide from 280 parts per million in 1750 to 412.5 parts per million in 2020, which is the average for the year. These greenhouse gases absorb and then re-radiate heat in Earth's atmosphere, which causes increased warming. The annual rate of increase in atmospheric carbon dioxide over the past 60 years is about 100 times faster than previous natural increases, such as those that occurred at the end of the last ice age, around 11,000 to 17,000 years ago. Aerosols, dust, and smoke come from both human and natural sources and have various effects on climate. Sulfate aerosols, which result from burning coal, biomass, and volcanic eruptions, tend to cool the Earth. Other kinds of particles, such as black carbon, have a warming effect. The global distribution of aerosols is being tracked from the ground as well as from satellites. Processes that can either amplify or diminish the effects of climate forcings are known as feedbacks. A feedback that increases an initial warming is called a positive feedback. A feedback that reduces an initial warming is a negative feedback. Clouds have an enormous impact on Earth's climate, reflecting about 1/3 of the total amount of sunlight that hits the Earth's atmosphere back into space. Even small changes in cloud amount, location, and type can have large consequences on the climate system. Global climate models show that precipitation will generally increase due to the increased amount of water held in a warmer atmosphere, but not in all regions. Some regions will become drier. Natural processes, such as tree growth, remove about half of carbon dioxide emissions from the atmosphere every year. The delicate balance between the absorption and release of carbon dioxide by the oceans and the world's great forested regions is the subject of research by many scientists. Ice is white for the most part and very reflective, in contrast to the ocean surface, which is dark and absorbs heat faster. As the atmosphere warms and sea ice melts, the darker ocean absorbs more heat, causes more sea ice to melt, and makes the Earth warmer overall. The ice albedo feedback is a very strong positive feedback. Climate tipping points occur when Earth's climate abruptly moves between relatively stable states. Due to the strong positive feedback of the ice albedo, if enough ice melts, it will cause Earth's surface to absorb more and more heat. Shrinking ice sheets contribute to sea level rise, and many hundreds of millions of people live near a coast. So our ability to predict sea level rise over the next century has substantial human and economic ramifications. Deposits of frozen methane a potent greenhouse gas, and carbon dioxide lie beneath permafrost in Arctic regions. About a quarter of the northern hemisphere is covered by permafrost. As the environment warms and the permafrost thaws, these deposits can be released into the atmosphere and present a risk of enhanced warming. The planet's average surface temperature has risen about 1.18 degrees centigrade or 2.12 degrees Fahrenheit since the late 19th century, a change driven largely by increased greenhouse gas emissions into the atmosphere. In the Intergovernmental Panel on Climate Change's sixth assessment report, released this year, 2021, they state, observed increases in well-mixed greenhouse gas concentrations since around 1750 are unequivocally caused by human activities. Since 1750, most of the warming has occurred in the past 40 years, with the 7 most recent years being the warmest on record. The visualization on the right of the slide shows how the distribution of land temperature anomalies has varied from 1951 to 2020. As the planet has warmed, we see the peak of the distribution shifting to the right, indicating an increase in global land temperature. The distribution of temperatures broadens as well. This broadening is most likely due to different regional warming, rather than increased temperature variability at any given location. Ice cores provide a unique contribution to our view of past climate because the bubbles within the ice capture the gas concentrations of our well-mixed atmosphere, while the ice itself records other properties. At the Earth's highest latitudes and altitudes, ice is typically the only environmental data available for scientists to reconstruct the climate hundreds to thousands of years ago. Ice cores have distinct layers in them that form throughout the years. With each passing year, snow falls over the ice sheets, and each layer of snow has a different texture and a different chemistry. With winter shows differing from summer snow. During the summer, when the sun is up for 24 hours, many days, the top layer of the snow changes in texture. As winter arrives and it turns cold and dark again, new snow falls on top of the summer snow, forming distinct layers. Each of these layers provides scientists with a vast amount of information about the climate each year. Ice cores can tell scientists about temperature, precipitation, atmospheric composition, volcanic activity, and even wind patterns. Researchers drill ice cores from deep inside the polar ice sheets in Greenland and Antarctica, sometimes more than 1.5 kilometers, as well as from high latitude ice caps and mountain glaciers. They collect ice cores in many locations around Earth to study regional climate variability and compare and differentiate that variability from global climate signals. Proportions of different oxygen and hydrogen isotopes provide information about ancient temperatures, and the air trapped in tiny bubbles can be analyzed to determine the level of atmospheric gases, such as carbon dioxide. The oldest ice cores from East Antarctica provide an 800,000-year-old record of Earth's climate. The sun can influence Earth's climate, and it does, but it isn't responsible for the warming trend we've seen over the recent decades. Subtle changes in Earth's orbit around the sun are responsible for the comings and goings of the ice ages, but the warming we've seen in recent decades is too rapid to be linked to changes in Earth's orbit and too large to be caused by solar activity. One of the ways scientists know the sun is not causing global warming comes from observing the amount of solar energy reaching the top of Earth's atmosphere. Since 1978, Scientists have been tracking incoming solar radiation using sensors on satellites, which tells us that there has been no upward trend in the amount of solar energy reaching our planet over these past few decades. A second way scientists know the sun is not causing global warming is that if the sun were responsible for global warming, we would expect to see warming throughout all layers of the atmosphere, from the surface to the upper atmosphere, or stratosphere. But what we actually see is warming at the surface and cooling in the stratosphere. This is consistent with the warming being caused by a buildup of heat-trapping gases near Earth's surface, and not by an increased amount of solar radiation received by Earth, measured in watts per square meter. The graph on the right compares global surface temperature changes, represented as the red line, and the sun's energy received by Earth, the yellow line, in watts per square meter since 1880. The lighter, thinner lines show the yearly levels, while the heavier, thicker lines show the 11-year average variations related to sunspot cycles. Looking at the lighter, thinner yellow lines, you can see the 11-year solar cycle. 11-year averages are used to reduce the year-to-year natural noise in the data, making the underlying trends more obvious. The amount of solar energy Earth receives has followed the sun's natural 11-year cycle with no net increase since the 1950s. Over that same period, global temperature has risen markedly. It is therefore extremely unlikely that the sun has caused the observed global temperature warming trend over the past half century. Milankovitch cycles include the shape of Earth's orbit, its eccentricity, the angle that Earth's axis is tilted with respect to Earth's orbital plane, known as its obliquity, and the direction that Earth's spin is pointed, known as its precession. These cycles affect the amount of sunlight and therefore energy that Earth absorbs from the sun. They provide a strong framework for understanding long-term changes in Earth's climate, including the beginning and end of ice ages throughout Earth's history. In the animation on the right of the slide, we see representations in the changes of eccentricity, which occur over 100,000 year cycles, Earth's axial precession, which occur over 26,000 year cycles, and changes in obliquity, which occur over 41,000 year cycles. But Milankovitch cycles can't explain all climate change that's occurred over the past 2.5 million years or so. And more importantly, they cannot account for the current period of rapid warming Earth has experienced since the pre-industrial period, the period between 1850 and 1900, and particularly since the mid-20th century. Milankovitch cycles operate again over long timescales, ranging from tens of thousands to hundreds of thousands of years. In contrast, Earth's current warming has taken place over timescales of decades to centuries. Over the last 150 years, Milankovitch cycles have not changed the amount of solar energy absorbed by Earth very much. In fact, NASA satellite observations show that over the last 40 years, solar radiation has actually decreased by a small amount. Second, Milankovitch cycles are just one factor that may contribute to climate change, both past and present. Even for ice age cycles, changes in the extent of ice sheets and atmospheric carbon dioxide have played important roles in driving the degree of temperature fluctuations over the last several million years. During past glacial cycles, the concentration of carbon dioxide in our atmosphere fluctuated from about 180 parts per million to 280 parts per million, as part of Milankovitch cycle-driven changes to Earth's climate. These fluctuations provided an important feedback to the total change in Earth's climate that took place during those cycles. Today, however, It's the direct input of carbon dioxide into the atmosphere from burning fossil fuels that's responsible for changing Earth's atmospheric composition over the last century, rather than climate feedbacks from the ocean or land caused by Milankovitch cycles. This relatively rapid warming of our climate due to human activities is happening in addition to the very slow changes to climate caused by Milankovitch cycles. Climate models indicate any forcing of Earth's climate due to Milankovitch cycles is overwhelmed when human activities cause the concentration of carbon dioxide in Earth's atmosphere to exceed about 350 parts per million. Scientists know of no natural changes to the equilibrium between the amount of solar radiation absorbed by the Earth and the amount of energy radiated back to space that can account for such a rapid period of global warming. Since 1750, the warming driven by greenhouse gases coming from humans burning fossil fuels is over 50 times greater than the slight extra warming coming from the sun itself over that same time interval. If Earth's current warming was due to the sun, scientists state we should expect temperatures in both the lower atmosphere, the troposphere, and the next layer of the atmosphere, the stratosphere, to warm. Instead, observations from balloons and satellites show Earth's surface and lower atmosphere have warmed, but the stratosphere has cooled. Finally, Earth is currently in an interglacial period, which is a period of milder climate between ice ages. If there were no human influences on climate, scientists say Earth's current orbital positions within the Milankovitch cycles predict our planet should be cooling, not warming, continuing a long-term cooling trend that began 6,000 years ago. Gases and dust particles thrown into the atmosphere during volcanic eruptions have influences on climate. Most of the particles spewed from volcanoes cool the planet by shading incoming solar radiation. The cooling effect can last for months to years, depending on the characteristics of the eruption. Volcanoes have caused global warming over millions of years during times in Earth's history when extreme amounts of volcanism occurred, releasing greenhouse gases into the atmosphere. Even though volcanoes are in specific places on Earth, their effects can be more widely distributed as gas, dust, and ash get into the atmosphere. Because of atmospheric circulation patterns, eruptions in the tropics can have an effect on the climate in both hemispheres, while eruptions at mid or high latitudes only have an impact on the hemisphere that they are within. Volcanoes also release large amounts of greenhouse gases, such as water vapor and carbon dioxide. The amounts put into the atmosphere from a large eruption doesn't change the global amounts of these gases very much. However, there have been times during Earth's history when intense volcanism has significantly increased the amount of carbon dioxide in the atmosphere and caused global warming. Overall, volcanoes release about 1% of the equivalent amount of carbon dioxide released by human activities. By comparison, human activities emit a Mount St. Helens eruption of carbon dioxide every 2.5 hours, and a Mount Pinatubo eruption of carbon dioxide twice daily. Life depends on, is shaped by, and affects climate. The essence of this principle is that life affects the climate system, and in turn, the climate dictates where and how species can survive. Life affects the composition of the atmosphere, and therefore the climate, because different life forms take in and release gases like carbon dioxide, methane, and oxygen at different rates. Climatic conditions help to shape various ecosystems and habitats around the globe. Life, including microbes, plants, and animals, is a major driver of the global carbon cycle and can influence global climate by modifying the chemical makeup of the atmosphere. Extinctions of species, both in the geologic past and in the present day, can be linked to changes in climate. Changes in climate will result in shifting ecosystems. It is not possible to predict the specific effects of climate change on each of the world's ecosystems, but biologists and ecologists are observing these changes across the planet. The visualization on the right shows Earth's biosphere data on ocean and land. In the Indian Ocean, we see changes in ocean color driven by chlorophyll A levels from phytoplankton. In northern latitudes, we can see how the great boreal forests of Siberia go through annual shifts of green up to senescence, and how the Sahel region in equatorial Africa shifts latitudinally with the seasons. Most of the energy that reaches Earth's surface is shortwave light, ultraviolet, visible, and infrared, which warms the surface and is transformed into long-wave infrared that radiates back toward space. Most of the gases in the atmosphere, more than 99.9%, do not trap the outgoing long-wave infrared radiation. They can, in effect, be zeroed out of the equation. However, the greenhouse gases in the atmosphere, such as water vapor, carbon dioxide, methane, and nitrogen oxides, are very powerful in absorbing the outgoing infrared radiation and re-radiating it in all directions. Part of the thermal re-radiation returns to Earth, causing the lower atmosphere to warm. Human activities, primarily the burning of fossil fuels, have fundamentally increased the concentration of greenhouse gases in Earth's atmosphere, warming the planet. Scientists attribute the global warming trend observed since the mid-20th century to the human expansion of the greenhouse effect. The video on the right shows a simplified animation of the greenhouse effect. Unlike nitrogen or oxygen, which make up most of our atmosphere, greenhouse gases, water vapor, carbon dioxide, methane, nitrous oxide, and fluorinated gases absorb thermal infrared energy, or heat, and release it gradually over time to space, and some portion back to the surface. Without this natural greenhouse effect, Earth's average annual temperature would be below freezing, instead of close to 15.5 degrees centigrade, which it is currently. The abundance of carbon in the atmosphere is reduced through seafloor accumulation of marine sediments and accumulation of plant biomass through photosynthesis, and is increased through deforestation and burning of fossil fuels. The diagram on the right shows the composition of Earth's atmosphere by molecular count, excluding water vapor. The upper pie chart shows Earth's atmosphere is composed of about 78% nitrogen, 21% oxygen, 0.9% argon. The lower pie chart represents trace gases that together compose about 0.043% of the atmosphere. Of this 0.043%, carbon dioxide is the dominant trace gas, comprising 0.04% of that total. The following slides will go into more depth on each of the major greenhouse gases. Water vapor is the most abundant greenhouse gas in the atmosphere. However, changes in its concentration is also considered to be a result of climate feedbacks related to the warming of the atmosphere, rather than a direct result of industrialization. The feedback loop in which water is involved is critically important to projecting future climate change. As the temperature of the atmosphere rises, more water is evaporated from ground storage, such as rivers, oceans, reservoirs, and the soil. Because the air is warmer, the absolute humidity can be higher. In essence, the air is able to hold more water when it's warmer, leading to more water vapor in the atmosphere. As a greenhouse gas, the higher concentration of water vapor is then able to absorb more thermal infrared energy radiated from the Earth, thus further warming the atmosphere. The warmer atmosphere can then hold more water vapor, and so on and so on. This is referred to a positive feedback loop. However, Huge scientific uncertainty exists in defining the extent and importance of this feedback loop. As water vapor increases in the atmosphere, more of it will eventually also condense into clouds, which are more able to reflect incoming solar radiation, thus allowing less energy to reach the Earth's surface and heat it up. The future monitoring of atmospheric processes involving water vapor will be critical to fully understand the feedbacks in the climate system leading to global climate change. The natural production and absorption of carbon dioxide is achieved through the terrestrial biosphere and the ocean. However, humankind has altered the natural carbon cycle by burning coal, oil, natural gas, and wood since the Industrial Revolution began in the mid-1700s. Each of these activities has increased in scale and distribution. Carbon dioxide was the first greenhouse gas demonstrated to be increasing in the atmospheric concentration, with the first conclusive measurements being made in the last half of the 20th century. Prior to the Industrial Revolution, concentrations were fairly stable at 280 parts per million. In May 2021, carbon dioxide concentrations were at 419 parts per million, an increase of approximately 49%. The atmospheric concentration has a marked seasonal oscillation that is mostly due to the greater extent of landmass in the northern hemisphere and its vegetation. A greater drawdown of carbon dioxide occurs in the northern hemisphere spring and summer as plants convert carbon dioxide to plant material through photosynthesis. It is then released again in the fall and winter during plant senescence in the northern hemisphere. Scripps' scientist Charles David Keeling initiated on-site measurements of carbon dioxide at NOAA's weather station on Mauna Loa in Hawaii in 1958. NOAA began taking measurements in 1974, and the two research institutions have made complementary, independent observations ever since. The highest monthly mean carbon dioxide value of the year occurs in May, just before plants in the northern hemisphere start to remove large amounts of carbon dioxide from the atmosphere during the growing season. In the northern fall, winter, and early spring, plants and soils give off carbon dioxide, causing levels to rise through May. Charles David Keeling was the first to observe this seasonal rise and subsequent fall in carbon dioxide levels every year, a dynamic which is now known as the Keeling curve. Keeling was also the first to recognize that despite the seasonal fluctuation, carbon dioxide levels were rising every year. In fact, every single year since the start of the measurements in 1958, carbon dioxide levels have been higher than the preceding year. The atmospheric burden of carbon dioxide is now comparable to where it was during the Pliocene climatic optimum between 4.1 and 4.5 million years ago, when carbon dioxide was close to or above 400 parts per million. During that time, over 4 million years ago, sea level was about 78 feet higher than today. The average temperature was 7 degrees Fahrenheit higher than in pre-industrial times, and studies indicate large forests occupied areas of the Arctic that are now tundra. The graph on the right depicts the upward trajectory of carbon dioxide in the atmosphere as measured at the Mauna Loa Atmospheric Baseline Observatory by NOAA and the Scripps Institution of Oceanography. Methane is an extremely effective absorber of radiation, though its atmospheric concentration is less than carbon dioxide and its lifetime in the atmosphere is brief, between 10 to 12 years, compared to other greenhouse gases such as carbon dioxide, nitrous oxide, and chlorofluorocarbons. Methane has both natural and anthropogenic sources. It is released as part of biological processes in low oxygen environments, such as in swamplands, or in rice production. Over the last 50 years, human activities such as growing rice, raising cattle, using natural gas, and mining coal have added to the atmospheric concentration of methane. Direct atmospheric measurement of atmospheric methane has been possible since the late 1970s, and its concentration rose from 1.52 parts per million volume in 1978 by around 1% per year to 1990. Since then, there has been little sustained increase. The October 2020 atmospheric concentration was approximately 1.89 parts per million volume. Concentrations of nitrous oxide also began to rise at the beginning of the Industrial Revolution and are understood to be produced by microbial processes in soil and water, including those reactions which occur in fertilizer containing nitrogen. Increasing use of these fertilizers has been made over the last century. Global concentration for nitrous oxide in October 2020 was 333 parts per billion. And in addition to agricultural sources for the gas, some industrial processes, such as fossil fuel-fired power plants, nylon production, nitric acid production, and vehicle emissions also contribute to its atmospheric load. Chlorofluorocarbons, or CFCs, have no natural source, but were entirely synthesized for such diverse uses as refrigerants, aerosol propellants, and cleaning solvents. Their creation was in 1928, and since then, concentrations of chlorofluorocarbons, or CFCs, in the atmosphere have been rising. Due to the discovery that they are able to destroy stratospheric ozone, a global effort to halt their production was undertaken and was extremely successful. So much so that levels of the major CFCs are now remaining level or declining. However, their long atmospheric lifetimes determine that some concentration of the CFCs will remain in the atmosphere for over 100 years. Since they are also a greenhouse gas, they are also of concern. Another set of synthesized compounds, called HFCs, or hydrofluorocarbons, are also greenhouse gases, though they are less stable in the atmosphere and therefore have a shorter lifetime and less of an impact as a greenhouse gas. Carbon dioxide is the most important of Earth's long-lived greenhouse gases. It absorbs less heat per molecule than the greenhouse gases methane or nitrous oxide, but it's more abundant and stays in the atmosphere longer, from 300 to 1,000 years. Increases in atmospheric carbon dioxide are responsible for about 2/3 of the total energy imbalance that is causing Earth's temperature to rise. Another reason carbon dioxide is important in the Earth system is that it dissolves into the ocean and reacts with water molecules, producing carbonic acid and lowering the ocean's pH. Since the start of the Industrial Revolution, the pH of the ocean's surface waters has dropped from 8.21 to 8.1. This drop in pH is called ocean acidification. Natural increases in carbon dioxide concentrations have periodically warmed Earth's temperature during ice age cycles over the past million years or more. Based on air bubbles trapped in 1.5-kilometer thick ice cores and other paleoclimatic climate evidence, we know that during the last ice age cycles of the past million years or so, carbon dioxide never exceeded 300 parts per million. Before the Industrial Revolution started in the mid-1700s, the global average amount of carbon dioxide was about 280 parts per million. The graph on the right shows the heating imbalance in watts per square meter relative to the year 1750, caused by all major human-produced greenhouse gases: carbon dioxide, methane, nitrous oxide, chlorofluorocarbons 11 and 12, and a group of 15 other minor contributors. Today's atmosphere absorbs about 3 extra watts of incoming solar energy over each square meter of Earth's surface. According to NOAA's annual greenhouse gas index, which is the RIGHT index, the combined heating influence of all major greenhouse gases has increased by 43% relative to 1990. This graph shows atmospheric carbon dioxide levels on the planet over the past 800,000 years. Carbon dioxide levels have not exceeded 310 parts per million, going back 800,000 years. The graph is based on the comparison of atmospheric samples contained in ice cores and more recent direct measurements, and provides evidence that atmospheric carbon dioxide has increased significantly since the Industrial Revolution. One can clearly see the abrupt rise in carbon dioxide levels from 1950 onward, and where we currently are at 412.5 parts per million, which was the average for the year 2020. This animation shows atmospheric carbon dioxide levels over the past 2 centuries. The amount of carbon dioxide released due to burning fossil fuels has been increasing since the start of the Industrial Revolution in the mid-18th century. One dot in the animation represents 1 metric ton of carbon dioxide. In 1800, less than 1 metric ton of CO2, carbon dioxide, was released each second. By 1900, that number had jumped to 62 metric tons per second, and by 2000, we were releasing 756 metric tons of carbon dioxide every second from burning fossil fuels. The following slides describe the evidence of rapid climate change. The planet's average surface temperature, again, has risen by about 1.18 degrees Celsius since the late 19th century, a change driven largely by increased carbon dioxide emissions into the atmosphere and other human activities. Notably, the 20 warmest years since that period have all occurred since 1981, and the 10 warmest years have all occurred in the last 12 years. The years 2016 and 2020 are tied for the warmest year on record since accurate measurements started being recorded in the mid-19th century. The global surface temperature is based on averaged air temperature data over land and sea surface temperatures observed from weather stations, buoys, ships, and satellites. The graph on the right shows the global annual average temperature measured over land and oceans. Red bars indicate temperatures above, and blue bars indicate temperatures below the 1901 to 2000 average temperature. The black line shows atmospheric carbon dioxide concentration in parts per million. One can see, since the late 1970s, an upward trend in both global temperature and carbon dioxide concentrations. The ocean has absorbed much of this increased heat, with the top 100 meters, about 328 feet, of ocean showing warming of more than 0.33 degrees Celsius since 1969. As Earth experiences a warming climate, we experience hotter air temperatures. The ocean does an excellent job of absorbing the extra heat from the atmosphere, delaying the full impact of global warming. The top few meters of the ocean store as much heat as Earth's entire atmosphere. So, as the planet warms, it's the ocean that gets most of the extra energy. More than 90% of the global warming is going into the ocean. While ocean heat content varies significantly from place to place and from year to year as a result of changing ocean currents and natural variability, there is a strong trend during the period of reliable measurements. Increasing heat content in the ocean is also consistent with sea level rise, which is occurring mostly as a result of thermal expansion of the ocean water as it warms. The graph on the right shows a time series of seasonal, red dots, and annual average, black line, global upper ocean heat content for the top 700 meters since 1955. We can see since the 1980s there has been a clear rise in global upper ocean heat content. Heating of the climate system has caused global mean sea level rise through ice melt on land and thermal expansion from ocean warming. According to the Intergovernmental Panel on Climate Change, thermal expansion explained 50% of sea level rise during 1971 to 2018, while ice loss from glaciers contributed 22%, ice sheets 20%, and changes in land water storage another 8%. Global mean sea level has been rising at an average rate of approximately 1.7 millimeters per year over the past 100 years, measured from tide gauge observations, which is significantly larger than the rate averaged over the last several thousand years. The rate in the last 2 decades, however, is nearly double that of the last century. The graph on the right shows annual averages of global sea level since 1870, shown in red. The blue dots represent tide gauge data, and the black dots are based on satellite observations. The inset in the bottom right shows global mean sea level rise since 1993, a period over which sea level rise has accelerated. Ice sheets are large bodies of ice on land that cover hundreds of thousands of square kilometers on Greenland and Antarctica. Greenland's ice sheets reaches more than 1.5 kilometers thick on average in the interior and contains an estimated 3 million cubic kilometers of ice, while Antarctica's ice is nearly 4.8 kilometers thick in some places, with a volume of about 25 million cubic kilometers of ice. Together, these ice sheets hold nearly 70% of the world's fresh water. When an ice sheet is in equilibrium, new snow accumulation is exactly balanced by melting at the surface, runoff, and calving at the ocean. Warmer air causes the ice to melt more quickly and flow more rapidly to the sea, especially in low elevation regions near the edges of the ice sheets. Observations of ice sheets losing mass are consistent with trends in small glaciers, as well as warming trends in global temperature during this period. Ultimately, as ice sheets shrink, the water they add to the ocean raises sea level around the world. According to the Intergovernmental Panel on Climate Change, melting of Greenland and Antarctic ice sheets accounted for about 1/3 of observed global sea level rise between 2006 and 2015. The graph on the right shows ice mass measurements by NASA's GRACE satellites since 2002. The rate of change measured by the satellites shows Greenland losing 277 billion metric tons of ice per year over the last 19 years. Warming temperatures lead to the melting of glaciers and ice sheets. Glaciers have been retreating worldwide for at least the last century. The rate of retreat has increased in the past decade. Only a few glaciers are advancing, and these are in locations where they were well below freezing and where increased precipitation has outpaced melting. The progressive disappearance of glaciers has implications not only for a rising global sea level, but also for water supplies in certain regions of Asia and South America. The graph on the right shows the cumulative decline in cubic miles in glacier ice worldwide. Satellite observations reveal that the amount of spring snow cover in the northern hemisphere has decreased over the past 5 decades, and the snow is melting earlier. This pattern is consistent with warmer global temperatures. Some of the largest declines have been observed in the spring and summer months. The black and white graph on the bottom of the slide shows the average of monthly snow cover extent anomalies over Northern Hemisphere lands, including Greenland, since November 1966. The colored graph on the right shows seasonal snow cover extent over Northern Hemisphere lands since winter of 1966 and 1967, calculated from NOAA snow maps. We can see in both the green and the red graphs that the snow accumulation has been going down in this period during these seasons. Both the extent and thickness of Arctic sea ice has declined rapidly over the last several decades. Arctic sea ice minimum extent has declined significantly since satellite measurements began in 1979, with the lowest values observed since 2012. Arctic sea ice reaches its minimum each September. September Arctic sea ice is now declining at a rate of 13.1% per decade relative to the 1981 to 2010 average. The animation on the right shows a time series of annual Arctic sea ice minimum since 1979, based on satellite observations. The 2012 sea ice extent is the lowest in the satellite record. One way climate changes can be assessed is by measuring the frequency of events considered extreme, which are among the most rare of temperature, precipitation, and storm intensity values. According to the IPCC, or the Intergovernmental Panel on Climate Change, it is virtually certain that hot extremes, including heat waves, have become more frequent and more intense across most land regions since the 1950s, while cold extremes, including cold waves, have become less frequent and less severe, with high confidence that human-induced climate change is the main driver of these changes. The frequency and intensity of heavy precipitation events have both increased since the 1950s over most land areas for which observational data are sufficient for trend analysis, high confidence, and human-induced climate change is likely the main driver. It is also likely that the global proportion of major tropical cyclone occurrence has increased over the last 4 decades, and the latitude where tropical cyclones in the western North Pacific reach their peak intensity has shifted northward. In the United States and elsewhere throughout the world, the number of record high temperature events has been increasing, while the number of record low temperature events has been decreasing since 1950. The planet has also witnessed increasing numbers of intense rainfall events. As mentioned earlier, the ocean absorbs about 30% of the carbon dioxide that is released in the atmosphere, where it dissolves into the ocean and reacts with water molecules, producing carbonic acid and lowering the ocean's pH. Since the start of the Industrial Revolution, the pH of the ocean's surface waters has dropped from 8.21 to 8.1. This drop in pH is called ocean acidification. A drop of 0.1 may not seem like a lot, but the pH scale is logarithmic. A 1-unit drop in pH means a 10-fold increase in acidity. A change of 0.1 means a roughly 30% increase in acidity. Increasing acidity interferes with the ability of marine life to extract calcium from the water to build their shells and skeletons. A consensus on climate change and its human cause exists. Multiple studies published in peer-reviewed scientific journals show that human activities are the primary cause of the observed climate warming trend over the past century. NOAA, NASA, the National Science Foundation, the National Research Council, and the United States Environmental Protection Agency have all published reports and fact sheets stating that Earth is warming mainly due to the increase in human-produced heat-trapping gases. Multiple studies published in peer-reviewed scientific journals show that 97% or more of actively publishing climate scientists agree. Climate warming trends over the past century are extremely likely due to human activities. In addition, most of the leading scientific organizations worldwide have issued public statements endorsing this position. One of the most definitive assessments of global climate science comes from the Intergovernmental Panel on Climate Change, or IPCC. Founded by the United Nations in 1988, the IPCC releases periodic reports, and each major release includes 3 volumes, one on the science, one on the impacts, and one on mitigation. Each volume is authored by a separate team of international experts who reviews, evaluates, and summarizes relevant research published since the prior report. Hundreds of leading experts in the different areas covered by IPCC reports volunteer their time and expertise as coordinating lead authors to produce these assessments. The following are some of the findings published by the IPCC in the Working Group 1 contribution to the 6th assessment report, which was released this year in 2021. It is unequivocal that human influence has warmed the atmosphere, ocean, and land. Widespread and rapid changes in the atmosphere, ocean, cryosphere, and biosphere have occurred. The scale of recent changes across the climate system as a whole and the present state of many aspects of the climate system are unprecedented over many centuries to many thousands of years. Human-induced climate change is already affecting many weather and climate extremes in every region across the globe. Evidence of observed changes in extremes such as heat waves, heavy precipitation, droughts, and tropical cyclones, and in particular their attribution to human influence, has strengthened since the 5th assessment report. Global surface temperature will continue to increase until at least the mid-century under all emission scenarios considered. Global warming of 1.5 degrees centigrade and 2 degrees centigrade will be exceeded during the 21st century unless deep reductions in carbon dioxide and other greenhouse gas emissions occur in the coming decades. Many changes due to past and future greenhouse gas emissions are irreversible for centuries to millennia, especially changes in the ocean, ice sheets, and global sea level. From a physical science perspective, limiting human-induced global warming to a specific level requires limiting cumulative carbon dioxide emissions, reaching at least net zero carbon dioxide emissions, along with strong reductions in other greenhouse gas emissions. In this next section, we'll be focusing on the role of Earth observations in climate change assessment. NASA Earth-observing satellites observe changes across the entire planet, from the atmosphere, biosphere, hydrosphere, cryosphere, and lithosphere. Each observing satellites provide consistent, timely, global, accurate measurements from the tropics to the polar regions. NASA conducts a program of breakthrough research on climate science, enhancing the ability of the international scientific community to advance global integrated Earth system science using space-based observations. The agency's research encompasses solar activity, sea level rise, the temperature of the atmosphere and the oceans, the state of the ozone layer, air pollution, and changes in sea ice and land ice. Instruments on NASA's Terra and Aqua satellites have provided the first global measurements of aerosols in our atmosphere, which come from natural sources such as volcanoes, dust storms, as well as man-made sources such as the burning of fossil fuels. Other instruments on board the Aura satellite study the processes that regulate the abundance of ozone in the atmosphere. Data from the GRACE and ICESat missions and from spaceborne radar show unexpectedly rapid changes in the Earth's great ice sheets, while the JASON 3, OSTM JASON 2, and JASON 1 missions have recorded a sea level rise of an average of 7.5 centimeters since 1992. NASA's Earth Observing System's weather instruments have demonstrated significant improvements in global forecast skill. The following slides will highlight the current fleet of operational NASA missions used for climate science. NASA's AURA mission obtains measurements of ozone, aerosols, and key gases to gain insights into the chemistry of our atmosphere. AURA flies in formation about 15 minutes behind Aqua in the A-Train satellite constellation, which we saw on the previous slide, which consists of several satellites flying in close proximity. AURA's 4 instruments study the atmosphere's chemistry and dynamics. AURA's instruments enable us to investigate questions about ozone trends, air quality changes, and their linkage to climate change, and provide accurate data for predictive models and provide useful information for local and national agency decision support systems. The United States Environmental Protection Agency monitors 6 criteria pollutants to make air quality forecasts. The AURA spacecraft monitors 5 of the 6 pollutants: ozone, carbon monoxide, aerosols, nitrogen dioxide, and sulfur dioxide. The Cloud Aerosol LiDAR and Infrared Pathfinder satellite observation, also known as CALIPSO, is a joint NASA-French mission. Observations from spaceborne LiDAR, combined with passive imagery, will lead to improved understanding of the role aerosols and clouds play in regulating the Earth's climate. CALIPSO also flies in the afternoon, or A-Train, satellite constellation along with AURA. Launched into Earth orbit on May 4, 2002, aboard NASA's Aqua satellite, the Atmospheric Infrared Sounder, or AIRS, provides data critical to the monitoring of Earth's atmosphere. AIRS data are improving weather forecast and advancing our understanding of Earth's climate. The AIRS instrument is the most advanced water vapor sensor ever built, and 60%, as I've said, of the greenhouse effect of the global atmosphere comes from water vapor. It also observes trace gases in the atmosphere, such as ozone, carbon monoxide, carbon dioxide, and methane. The Advanced Microwave Scanning Radiometer, or AMSR, has operated on 3 satellites, 1 on Aqua and the other 2 on spacecraft operated by the Japan Aerospace Exploration Agency, also known as JAXA. AMSR-E measures geophysical parameters supporting several global change science and monitoring efforts, including precipitation, oceanic water vapor, cloud water, near-surface wind speed, sea surface temperature, soil moisture, snow cover, and sea ice parameters. All of these instruments are critical to understanding the Earth's climate. The visualization on the right shows the global distribution and variation of the concentration of mid-tropospheric carbon dioxide observed by AIRS. For comparison, it is overlaid by a graph of the seasonal variation and interannual increase of carbon dioxide observed at the Mauna Loa Observatory. Also on the Aqua satellite, the Clouds and Earth's Radiant Energy System, or CERES, instrument measures both solar reflected and Earth emitted radiation from the top of the atmosphere to the Earth's surface, providing measurements of the spatial and temporal distribution of Earth's radiation budget. NASA launched the first CERES mission aboard the Tropical Rainfall Measuring Mission satellite, or TRMM, in November 1997. There are currently 6 CERES instruments on NASA and NOAA satellites. CERES will measure the energy at the top of the atmosphere, as well as estimate energy levels in the atmosphere and at the Earth's surface. Using information from very high-resolution cloud imaging instruments on the same spacecraft, CERES will also determine cloud properties, including altitude, thickness, and the size of the cloud particles. All of these measurements are critical for advancing the understanding of the Earth's total climate system and the accuracy of climate prediction models. The graph on the right of the slide shows a plotted view of planetary heat uptake since the beginning of the Ceres data record, showing an oscillating monthly mean, shown in yellow, and a 12-month running average, which is the red line. These data show how much energy is added by Earth during the period Ceres instruments have been operating. Also on the Aqua satellite is the Moderate Resolution Imaging Spectroradiometer, also known as MODIS. With its sweeping 2,330 kilometer wide viewing swath, MODIS observes every point on the planet every 1 to 2 days in 36 discrete spectral bands. This wide spatial coverage enables MODIS, together with MISR and Ceres, to help scientists determine the impact of clouds and aerosols on the Earth's energy budget. MODIS also measures the properties of aerosols that enter the atmosphere from man-made sources like pollution and biomass burning, as well as natural resources such as dust storms, volcanic eruptions, and forest fires. MODIS helps scientists determine the amount of water vapor in a column of the atmosphere and the vertical distribution of temperature and water vapor, measurements crucial to understanding Earth's climate system. MODIS is ideal for monitoring large-scale changes in the biosphere that are yielding new insights into the workings of the global carbon cycle. Coupled with the sensor's surface temperature measurements, MODIS measurements of the biosphere are helping scientists track the sources and sinks of carbon dioxide in response to climate changes. Together with Suomi NPP's VIRS instrument, MODIS provides more than 20 years of aerosol information, climate forcing, and surface temperature trends, which is the impact. Because clouds have such a large impact on Earth's radiation budget, even small changes in cloud abundance or distribution could alter the climate more than the anticipated changes in greenhouse gases, anthropogenic aerosols, and other factors associated with global change. CloudSat was selected as a NASA Earth System Science Pathfinder satellite mission in 1999 to provide observations necessary to advance our understanding of cloud abundance, distribution, structure, and radiative properties. Since 2006, CloudSat has flown the first satellite-based millimeter wavelength cloud radar, a radar that is more than 1,000 times more sensitive than existing weather radars. CloudSat is studying clouds in detail to better characterize the role they play in regulating Earth's climate. CloudSat is providing the first direct global survey of the vertical structure and overlap of cloud systems and their liquid and ice water contents. Data return should lead to improved cloud representations in atmospheric models, helping improve the accuracy of weather forecasts and climate predictions made using these models. CloudSat and Calypso, mentioned on the previous slide, were designed to complement each other. They launched together on the same rocket in 2006 and are currently in the same C-Train orbit. Installed on the International Space Station, the Global Ecosystem Dynamics Investigation, or GEDI instrument, produces high-resolution laser-ranging observations of the three-dimensional structure of the Earth. GEDI laser altimetry observations provide unprecedented measurements of the Earth's surface, coastal waters, and temperate glaciers. GEDI observes wasting subpolar and land ice, including the high mountain Asia and Patagonia glaciers and ice caps, which contribute to sea level. The science of GEDI is centered on answering three key scientific questions. What is the carbon balance of the Earth's forests? How will the land surface mitigate atmospheric carbon dioxide concentrations in the future? And how does forest structure affect habitat quality and biodiversity? The distribution of the world's rainfall is shifting as our climate changes. As the troposphere becomes warmer, evaporation rates increase, which leads to an increase in the amount of moisture circulating. When the troposphere has more moisture, more intense precipitation occurs. thus potentially triggering more flooding over land. Conversely, in other areas, warmer temperatures may lead to increased drying, accelerating the onset of drought. The Global Precipitation Measurement, or GPM mission, is an international network of satellites that provide next-generation global observations of rain and snow. Building upon the success of NASA's Tropical Rainfall Measuring Mission, or TRMM, the GPN concept centers on the deployment of a core observatory satellite carrying an advanced radar radiometer system to measure precipitation from space and serve as a reference standard to unify precipitation measurements from a constellation of research and operational satellites. The key information offered by both TRMM and GPM helps scientists more accurately estimate the rate of water transfer within the Earth's atmosphere and on the surface. It also reconciles the different parts of the overall water budget. By providing measurements of surface water fluxes, cloud precipitation microphysics, and latent heat release in the atmosphere, GPM advances Earth system modeling and analysis. More accurate global precipitation estimates improve the accuracy and effectiveness of climate models and advance understanding of climate sensitivity and future climate change. The visualization on the right is from the iMERGE algorithm, which combines information from the GPM satellite constellation to estimate precipitation over the majority of the Earth's surface. The Gravity Recovery and Climate Experiment Follow-On, or GRACE Follow-On mission, is a partnership between NASA and the German Research Center for Geosciences. GRACE Follow-On is the successor to the original GRACE mission, which orbited Earth from 2002 to 2017. GRACE Follow-On will continue the work of tracking Earth's water movement to monitor changes in underground water storage, the amount of water in large lakes and rivers, soil moisture, ice sheets, and glaciers, and sea level caused by the addition of water to the ocean. These discoveries provide a unique view of Earth's climate and have far-reaching benefits to society and the world's population. As the visualization on the right shows, GRACE Follow-On's raw data will be a series of measurements showing how far apart two satellites are from each other. The twin satellites follow each other in orbit around the Earth, separated by about 220 kilometers. They will constantly send microwave signals to each other to measure the distance between them. As the pair circles the Earth, areas of slightly stronger gravity, greater mass concentration, affect the lead satellite first, pulling it away from the trailing satellite. As the satellites continue, the trailing satellite is pulled toward the lead satellite as it passes over the gravity anomaly. This change in distance would certainly be imperceptible to our eyes, but the extremely precise microwave ranging system on GRACE Follow-On is designed to detect minuscule changes in the distance between the satellites. A highly accurate measuring device, known as an accelerometer, located at each satellite's center of mass, measures the non-gravitational accelerations, such as those due to atmospheric drag, so that only accelerations caused by gravity are considered. Satellite Global Positioning System receivers determine the exact position of the satellite over the Earth to within a centimeter or less. All this information from the satellites will be used to construct monthly maps of the Earth's average gravity field, offering details of how mass, in most cases water, either frozen or liquid, is moving around the planet. Earth's frozen regions, the cryosphere, are changing rapidly in our warming climate. The Ice Cloud and Land Elevation Satellite 2, or ICESat-2 mission, will provide scientists with height measurements that create a global portrait of Earth's third dimension, gathering data that can precisely track changes of terrain, including glaciers, sea ice, forests, and more. ICESat-2 carries a laser altimeter called ATLAS that allows scientists to measure the elevation of ice sheets, glaciers, and sea ice. The mission will help scientists investigate how the Earth's cryosphere is changing in a warming climate. The mission has 4 science objectives: measure melting ice sheets and investigate how this affects sea level rise, measure and investigate changes in the mass of ice sheets and glaciers, estimate and study sea ice thickness, and measure the height of vegetation in forests and other ecosystems worldwide. The graph on the right shows elevation measurements acquired by ICESat-2 on October 17, 2018, showing the height of the sea ice along an orbital path over the Weddell Sea. For reference, the orbital path is laid over a natural color image acquired by MODIS on the same day. To gather long-term information about the global ocean and currents, orbiting instruments must take extremely precise measurements of the height of the ocean surface, commonly called sea level, above the center of the Earth. This is referred to as ocean surface topography. Ocean surface topography data contain information that has significant practical applications in such areas as the study of worldwide weather and climate patterns, the monitoring of shoreline evolution, and the protection of ocean fisheries. JASON-3 is the fourth mission in the US-European series of satellite missions that measure the height of the ocean's surface using radar altimetry going back to 1992. The measurements provide scientists with critical information about circulation patterns in the ocean and both global and regional changes in sea level and the climate implications of a warming world. For nearly 3 decades, satellite altimeters have provided a precise, continuous record of global sea level with excellent spatial and temporal resolution. Landsat is a joint NASA-USGS mission. Currently, there are 3 Landsat satellites in orbit, Landsat 7, 8, and 9, which just launched 2 days ago on September 27th. The data from Landsat spacecraft constitute the longest record of coastal regions, polar ice, islands, and continental areas as seen from space. The missions characterize and monitor land cover use and change over time for global climate research, polar studies, and the impacts of natural events, as well as human activities on Earth's surface. As previously stated, carbon dioxide is one of the primary greenhouse gases on Earth. The nature and the locations of the sinks that absorb about half of the human-produced carbon dioxide are currently not well known and present important yet unanswered questions. The Orbiting Carbon Observatory 2, or OCO2 measurements, will be able to quantify carbon dioxide variability over the seasonal cycles year after year, and will provide the global coverage, spatial resolution, and accuracy to provide a basis to characterize and monitor the geographic distribution of carbon dioxide sources and sinks and quantify their variability. Based on these measurements, scientists will map the natural and man-made processes that regulate the exchange of carbon dioxide between the Earth's surface and the atmosphere on both regional to continental scales. These measurements will allow reliable forecasts of the atmospheric carbon dioxide abundance and its impact on the Earth's climate. The OCO2 mission will contribute to a large number of additional scientific investigations that are related to the global carbon cycle. This enhanced understanding is essential for improving predictions of future atmospheric carbon dioxide increases and their impact on Earth's climate. Rising seas are one of the most distinctive and potentially devastating effects of Earth's warming climate. Measuring and understanding changes in sea level allows us to assess the vulnerability of coastal cities and towns to flooding as we look toward the future. Precise sea level measurements can also be used to track ocean currents, which transport heat from one part of the planet to another, which in turn influences Earth's weather patterns. An uninterrupted series of satellites has collected sea level measurements for nearly 30 years. The Copernicus Sentinel-6 JASON Continuity of Service mission consists of 2 identical satellites that will be launched 5 years apart. The first spacecraft is Sentinel-6 Michael Freilich, named for the former director of NASA's Earth Science Division. Michael Freilich, he was a pioneer in oceanography from space and dedicated his life to better understanding the Earth, with the goal of improving the lives of those who call it home. Sentinel-6 Michael Freilich launched on November 21st, 2020. Its twin satellite is slated for liftoff in 2025. Both satellites will use a radar altimeter to measure sea level down to the centimeter for more than 90% of the world's oceans. The data they collect will add to a long-term data set that began with a joint US-French effort called TOPEX Poseidon that launched in 1992. The Soil Moisture Active-Passive, or SMAP mission, is an orbiting observatory that measures the amount of water in the surface soil everywhere on Earth every 2 to 3 days. SMAP will produce global maps of soil moisture. Scientists will use these to help improve our understanding of how water, energy, and carbon fluxes in its various forms maintain our climate and environment. The amount of water that evaporates from the land surface into the atmosphere depends on the soil moisture. Soil moisture information is key to understanding the flows of water and heat energy between the surface and atmosphere that impact weather and climate. SMAP data acquired since April 2015 has provided ample information about soil moisture variability at both regional and global scales. Frequent and reliable soil moisture measurements from SMAP will help improve the predictive capability of weather and climate models. The animation on the right shows SMAP launching and collecting global soil moisture data. Understanding, monitoring, and predicting the course of long-term climate change and short-term weather conditions remain tasks of profound importance. Over the last 2 decades, NASA has launched a series of satellites known collectively as the Earth Observing System that has provided critical insights into the dynamics of the entire Earth system. The Suomi National Polar Orbiting Partnership, or Suomi NPP, serves as a bridge between the Earth Observing System satellites and the series of Joint Polar Satellite System, or JPSS satellites, overseen by NOAA. Suomi NPP represents the gateway to the creation of a U.S. climate monitoring system, collecting both climate and operational weather data, and continuing data records that are critical for global climate change science. The mission maintains a global record of atmospheric, land surface, and sea surface temperatures critical to understanding the long-term dynamics of climate change. 5 instruments on Suomi NPP monitor changes to Earth's sea ice, land ice, and glaciers to track the pace of climate change. The VIIRS instrument on Suomi NPP extends the long-term data records started by the MODIS instruments still operating on both Aqua and Terra satellites. The Terra satellite is the flagship of NASA's Earth Observing System, providing global data on the state of the atmosphere, land, and oceans, and their interactions with solar radiation and with one another. Terra's 5 instruments, including the MODIS instrument, provide important climate measurements that record how Earth's energy budget is changing. The satellite launched on December 18, 1999, and has provided near global coverage every 1 to 2 days for almost 22 years. 4 Terra instruments, ASTER, CERES, MISR, and MODIS, work together to monitor how clouds are changing, both in response to climate change and natural climate variability due to El Niño and La Niña, or changes in solar activity. Terra instruments, CERA, MISR, and MODIS, monitor aerosol concentrations, identify aerosol types and sources, and monitor how aerosols are affecting the climate. Snow and ice reflect energy, which helps keep the climate cool. Terra instruments record snow and ice extent using both ASTER and MODIS, and track the amount of energy reflected into space from snow and ice, which is the CERES instrument. The U.S. Environmental Protection Agency, NOAA, and other atmospheric monitoring agencies use MISR, MODIS, and MOPIT for air quality measurements. The U.S. Forest Service, the U.S. Department of Agriculture, the U.S. Environmental Protection Agency, as well as international fire monitoring communities use ASTER, MISR, and MODIS for forest fire monitoring. Near real-time data from the MODIS Rapid Response System are used by federal and regional stakeholders to assess and monitor forest fires. The The Global Modeling and Assimilation Office, or GMAO, is a NASA organization that uses computer models and data assimilation techniques to enhance NASA's program of Earth observations. The Modern Era Retrospective Analysis for Research and Applications version 2, or MERA-2, is a global atmospheric reanalysis produced by GMAO. It spans the satellite observing era from 1980 to the present. The goals of MERA-2 are to provide a regularly gridded, homogeneous record of the global atmosphere and to incorporate additional aspects of the climate system, including trace gas constituents, stratospheric ozone, and improved land surface representation and cryospheric processes. MERA-2 is also the first satellite-era global reanalysis to assimilate space-based observations of aerosols and represent their interactions with other physical processes of the climate system. MERA-2 is intended to replace the original MERA product and reflects recent advances in atmospheric modeling and data assimilation. The animation on the right shows a record daily rainfall event starting on July 21, 2018. Throughout the multi-day precipitation event, a subtropical high-pressure system was present over the Atlantic Ocean, and a digging trough extended south into the Gulf of Mexico and north to the east coast of the United States. Both features helped guide the transport of water vapor into the Maryland area, as evident in the animation. This transport of water led to a catastrophic flooding event that basically flooded the lower city of Ellicott City in the state of Maryland. The Goddard Earth Observing System, or GEOS, family of models is used by the GMAO for applications across a wide range of spatial scales, from kilometers to many tens of kilometers. GEOS is an atmospheric model used to study the physics of the atmosphere in both the short-term weather and mid to long-term climate. The GEOS-5 model normally runs at a resolution of about 28 kilometers per pixel to study the connections between weather and climate. It can run globally at 3.5 kilometers, making it one of the most detailed global atmospheric models in the world. The GEOS-5 model, like all weather and climate models, uses mathematical equations that represent physical processes, like precipitation and cloud processes, to calculate what the atmosphere will do. Actual measurements of physical properties, like temperature, moisture, and winds, are routinely folded into the model to keep the simulation as close to the real world as possible. The millions of calculations involved in creating such a detailed global model require thousands of computer processors. The GEOS-5 model runs on the Discover supercomputer in the NASA Center for Climate Simulation at Goddard Space Flight Center. NASA climate scientists use GEOS-5 to predict climate over the span of a few decades. The GISS Model E is a long-term climate model also running on Discover. Model E is currently being used to simulate climate between about 1000 AD and 2100 AD. The largest project running on the supercomputer is MERA-2, which I previously mentioned, in which GEOS-5 integrates more than 50 billion observations, mostly from Earth-observing satellites, into a single model simulation of climate from 1979 to the present. The following section focuses on monitoring climate change impacts using NASA data. As mentioned in the previous section when describing satellite missions, since 1992, NASA has been using radar altimetry to measure sea surface height to determine global mean sea level. This is a record length of roughly 30 years where we can understand the changes that are occurring within the climate system. This record is one of the crowning achievements for sea level science and for engineering at NASA. Because of this really long, continuous record, with one satellite mission overlapping the next, NASA has been able to build an understanding of where and when sea level has been changing across the planet. These data build off the records collected from tide gauge stations from around the world, which have measured the daily high and low tides for more than a century. If we compare what we see during the satellite record to what we see in the past over the 20th century, we can start to see and get some context for the satellite record itself. In the graph, if you look at the period from around 1960 to 1970, global mean sea level is actually relatively flat. And the reason for that is that a lot of dams were being built around the world. A lot of the water that would have been going into the ocean was being trapped on land. It actually caused a decrease in sea level over that time period. But since about 1970, we've seen a persistent rise and consistent acceleration in sea level rise. And that's really the time period that we see the satellite altimeter record imprinted upon. With satellite observations, we can understand not just how fast sea level is increasing, but also why it's increasing. If we can understand why it's increasing, we can make better assessments of what might be happening in the future. If we understand the contribution from ice and the contribution from thermal expansion of the oceans, those two things together should add up to give us the total sea level that we see now and potentially will see in the future. We have observing systems for each of these. For ice, we have GRACE and GRACE follow-on, which we've discussed previously. For thermal expansion, we have the Argo profiling floats. And for total sea level, we have satellite altimetry going back to 1992 and continuing through to JASON-2 and Sentinel-6 Michael Freilich today. As mentioned previously, the GRACE and GRACE follow-on missions monitor changes in underground water storage. The amount of water in large lakes and rivers, soil moisture, ice sheets and glaciers, and sea level caused by the addition of water to the ocean. One of the main reasons that gravity is changing here on Earth is because of changes in our ice mass. If we are talking about the big ice sheets associated with Greenland and Antarctica, when they start to lose ice, GRACE and GRACE follow-on are able to observe that. These satellites can tell us how much ice is being lost across Earth's ice sheets and glaciers. They also tell us about the movement of water on Earth. NASA takes these measurements and combines them all to understand how much ice is being lost across the planet and how much water is going into the oceans. If we average all that together across the planet, we're observing a rate of change of about 2 millimeters per year from 2002 until the present. That is ice contribution to global mean sea level. The animation on the right shows how the mass of the Greenland ice sheet has rapidly declined in the last several years due to surface melting and iceberg calving. Research based on observations from the GRACE and GRACE follow-on satellites indicates that between 2002 and 2020, Greenland shed approximately 280 gigatons of ice per year, causing global sea level to rise by 0.8 millimeters or 0.03 inches per year. Since 2/3 of our global mean sea level contribution is coming from ice, this means that we should have about 1/3 coming from thermal expansion of the oceans. To determine thermal expansion of the oceans, scientists use Argo profiling floats. Argo is an international program that collects information from inside the ocean using a fleet of robotic instruments that drift with the ocean currents and move up and down between the surface and a mid-water level. Each float spends almost all of its life below the surface of the ocean. The data that Argo collects describes the temperature and salinity of the water, and some of the floats measure other properties that describe the biology and chemistry of the ocean. The main reason for collecting these data is to help us understand the ocean's role in Earth's climate, and so be able to make improved estimates of how it will change in the future. Each Argo float is launched from a ship. The float's weight is carefully adjusted so that as it sinks, it eventually stabilizes at a preset level, usually 1 kilometer below the surface of the ocean. 10 days later, an internal battery-driven pump transfers oil between a reservoir inside the float and an external bladder. This makes the float first descend to 2 kilometers and then return to the surface, measuring ocean properties as it rises. The data and the float position are relayed to satellites and then onto receiving stations onshore. The float then sinks again to repeat the 10-day cycle until its batteries are exhausted. From these measurements, we are able to estimate the impact of thermal expansion on sea level rise. When you take the data collected from Argo floats and add them together, and then average them, you end up getting a rate of change associated with thermal expansion. Another word for that is steric change, or steric height. Steric change means that the ocean is expanding due to expansion of water molecules. That rate of change shown on the graph is about 1.1 millimeters per year. And I do apologize as this graph is outdated, and the current rate of change is about 1.3 millimeters per year. The graph shown here is a summation of the previous slides. The y-axis represents sea level rise in millimeters, and the x-axis represents time from 1993 to 2020. The blue line shows global mean sea level recorded from satellite altimetry dating back to 1993. We can see a clear trend in sea level rise from that time. The orange line at the bottom of the graph shows thermal expansion, or steric change, recorded from Argo floats. The green line is showing the contribution to ocean mass from glaciers and ice sheets observed from the GRACE and GRACE follow-on missions. The yellow line is the summation of thermal expansion and global ocean mass, which overlaps quite well with the global mean sea level. This is one of the ways we can close the budget and understand why sea level is changing on a global scale. This is just one example of how NASA satellite missions are contributing to our understanding of the effects of climate change on a global scale. Well, it's all good to know that sea level rise is occurring at the global scale, but how does one plan at the local level? What if you're living along the coast of Madagascar or Japan? The global number is important. It tells us how the climate is warming, how Earth and the ocean is changing, but really, you want to know how much sea level is changing off your own coast. The ocean does not behave like a bathtub, and there is a lot of variability on a wide range of spatial and temporal scales. Natural processes like El Nino and La Nina greatly affect ocean circulation and sea level height. Looking at the image on the slide showing sea surface height changes from 1992 to 2019 in centimeters, we see that anywhere that's white, there's basically no sea level increase between that period from 1992 to 2019. That means sea level stayed relatively flat. Anything yellow, orange, or red has shown where sea level has increased. One important thing to note here is that over the past 3 decades, sea level has increased almost everywhere. Yes, there are regions where sea level has gone down a bit for a variety of different reasons, but sea level has generally gone up on a global scale, not just on the global average, but regionally as well. The other thing to note is that the rate of change does vary quite a bit. Focusing on North America, if you look at the east coast of the United States, the Gulf of Mexico, and the Caribbean, you see quite a bit of dark orange approaching red. Looking off the west coast of the United States, you see much lighter colors, actually even approaching near flat sea level rise over the past 30 years, since satellite altimetry has been keeping records. The next thing we will cover are ice sheet fingerprints. Because of the gravity changes that occur when ice melts, the water that comes from the melting ice does not fill up the ocean the same everywhere. This is a surprising factor. The top panel on this slide is showing the case when we lose ice from Greenland. What's interesting to note is that immediately around Greenland, sea level actually falls. Because we have less ice on Greenland, there's less of a gravitational pull toward that ice sheet. Sea level starts to spread out away from the ice sheet. So the further you are away from the source of ice melt, in this case, the further you are away from Greenland in the top panel, the more ice melt in Greenland will contribute to one sea level rise. If you look off the eastern coast of South America, for instance, where you have the dark red at the top panel, Greenland ice melt actually affects that part of the planet more than any other. It's surprising if we're talking about, let's say, the Gulf of Mexico and the Caribbean, we actually get less than the global average contribution from Greenland. So it affects regional sea level some, but not as much as it will in other parts of the planet. Now, if we look at the Antarctic ice sheet in the bottom panel, you see the same thing. When we're losing ice masses, especially from the West Antarctic ice sheet, lower sea level actually follows. And if you look at the contribution off of South America from ice melt in Antarctica, you actually have less than the global average and potentially even a drop in sea level for the very southern parts of South America. If you look further north, towards North America, we actually see a higher than global average increase in sea level associated with Antarctic ice melt. It's not always obvious where this water will go, but from a planning perspective, it's very critical. If you are in New York, for instance, you are very concerned about ice melt from the West Antarctic ice sheet because you know you're going to get hit really hard by that melt in the future. If you see a projection of a huge increase from ice melt there, then you're going to see this potentially very rapid increase in sea level off the east coast of the United States in the future. We can look at this one other way as well. On this slide, we're breaking down regional sea level changes by two cities, New York City on the east coast of the United States and Sydney on the east coast of Australia. The tables below each city show the different sources of where ice is melting from. In both cases, the global contribution of ice melt is the same. GRACE is measuring that global contribution from glaciers and ice sheet melt, which is about 2 millimeters per year, but it's not broken out evenly between these two locations. New York sees less of a contribution from ice melt than Sydney does. Not only that, the contribution from different sources is dramatically different. If we look specifically at the contributions from Greenland, you can see that Greenland contributes a little over 0.3 millimeters per year to New York City. On the other hand, it contributes about 0.7 millimeters per year to Sydney. It's almost double the contribution in terms of ice melt from Greenland in these two locations. It's really important that we're able to understand these ice sheet fingerprints and their contribution to regional sea level change. I'm going to shift gears here. We've talked about the ocean and that we have natural variability such as El Nino and La Nina, and that we have global sea level rise. But we should also discuss subsidence. Sea level is going up, but land could also potentially be going down. And in some locations, that subsidence that we're seeing is at the same level or even greater than what we see in terms of sea level rise. So understanding the subsidence is really critical. This is what we call relative sea level, and subsidence contributes to that relative sea level change. Groundwater withdrawal is one of the factors contributing to coastal subsidence. In coastal communities, a lot of times we're pumping out water directly below us. As we start to remove that water, it doesn't get replaced or recharged in the same way, and the land can start to sink. This is where we see subsidence occur. Another way subsidence can occur is through plate tectonics. This takes place over very short time periods if an earthquake occurs or there's tectonic movement, which can also lead to subsidence. There's a variety of ways that we can measure subsidence. One is to use GPS. If we have a GPS station in some of these locations, we can understand how the land is moving up and down. The way we measure subsidence from space is using interferometric synthetic aperture radar, or INSAR for short. The SAR interferometry technique uses two SAR images of the same area acquired at different times and interferes or differences them, resulting in maps called interferograms that show ground surface displacement between the two time periods. An example of this is illustrated in the rendering in the upper right of the slide. One of the satellite missions used to measure subsidence is the European Space Agency's Sentinel-1 spacecrafts. A future joint satellite mission between NASA and ISRO, named NISAR, will be able to generate interferograms as well once it's launched in 2023. I've talked about satellites used in understanding the underlying science of sea level change, the processes they measure, and gave you an indication of how you put these pieces together to make an evaluation. So how does NASA provide this useful information to decision makers? It requires integrated assessments in order to get this into the hands of planners and to those that actually need this information. To provide this useful information to decision makers, as well as to the general public, in 2014, NASA created a sea level change team. This team is comprised of 70+ scientists from government and academia from throughout the United States. The Sea Level Change team has a web portal at sealevel.nasa.gov. The web portal provides online tools and guidance with easy access to the underlying data, as well as to the satellite data. The team has two overarching goals. One is to provide improved forecasts of sea level across a range of timescales. That's really a scientific goal. The second goal is to connect with practitioners and stakeholders to provide useful sea level information. It's how they take the improved scientific understanding and actually generate guidance that's useful. The web portal at sealevel.nasa.gov was created to communicate the understanding that was obtained from these efforts and to provide an outlet for sharing data and guidance to the general public. This slide provides links to the many web tools created by NASA's Sea Level Change team. We hope you will explore for yourself to learn how you can use these tools for your own research and better understand how sea level changes will impact the planet, both regionally and globally. The following slides show how NASA is contributing to climate change decision-making. NASA is an expert in climate and Earth science. While its role is not to set climate policy or prescribe particular responses or solutions to climate change, its purview does include providing the robust scientific data needed to understand climate change and evaluating the impact of efforts to address it. NASA then makes this information available to the global community, the public, policy, and decision makers, and scientific and planning agencies around the world. The agency's research encompasses solar activity, sea level rise, the temperature of the atmosphere and the oceans, the state of the ozone layer, air pollution, and changes in sea ice and land ice. NASA scientists regularly appear in the mainstream media as climate experts. Climate change is one of the most complex issues facing us today. It involves many dimensions: science, economics, society, politics, and moral and ethical questions, and is a global problem felt on local scales that will be around for decades and centuries to come. Carbon dioxide, the heat-trapping greenhouse gas that has driven recent global warming, lingers in the atmosphere for hundreds of years, and the planet, especially the oceans, takes a while to respond to warming. So even if we stopped emitting all greenhouse gases today, global warming and climate change will continue to affect future generations. In this way, humanity is committed to some level of climate change. How much climate change? That will be determined by how our emissions continue and exactly how our climate system responds to those emissions. Despite increasing awareness of climate change, our emissions of greenhouse gases continue on a relentless rise. In 2013, the daily level of carbon dioxide in the atmosphere surpassed 400 parts per million for the first time in human history. The last time levels were that high was about 3 to 5 million years ago during the Pliocene epoch. Because we are already committed to some level of climate change, responding to climate change involves a two-pronged approach. Reducing emissions of and stabilizing the levels of heat-trapping greenhouse gases in the atmosphere is what we refer to as mitigation. Adapting to the climate change already in the pipeline is what we refer to as adaptation. Mitigation refers to reducing climate change, which involves reducing the flow of heat-trapping greenhouse gases into the atmosphere, either by reducing sources of these gases, for example, the burning of fossil fuels for electricity, heat, or transport, or enhancing the sinks that accumulate and store these gases, such as the oceans, forests, and soil. The goal of mitigation is to avoid significant human interference with the climate system and stabilize greenhouse gas levels in a time frame sufficient to allow ecosystems to adapt naturally to climate change, ensure that food production is not threatened, and to enable economic development to proceed in a sustainable manner. Adaptation refers to adapting to life in a changing climate and involves adjusting to actual or expected future climate. The goal is to reduce our vulnerability to the harmful effects of climate change, like sea level encroachment, more intense extreme weather events, or food insecurity. It also encompasses making the most of any potential beneficial opportunities associated with climate change. For example, longer growing seasons, or increased yields in some regions. Throughout history, people and societies have adjusted to and coped with changes in climate and extremes with varying degrees of success. Climate change, drought in particular, has been at least partly responsible for the rise and fall of civilizations. Earth's climate has been relatively stable for the past 12,000 years, and this stability has been crucial for the development of our modern civilization and life as we know it. Modern life is tailored to the stable climate we have been accustomed to. As our climate changes, we'll have to learn to adapt. The faster the climate changes, the harder it could be. While climate change is a global issue, it is felt on a local scale. Cities and municipalities are therefore at the front line of adaptation. In the absence of national or international climate policy direction, cities and local communities around the world have been focusing on solving their own climate problems. They are working to build flood defenses, plan for heat waves and higher temperatures, install water-permeable pavements to better deal with floods and stormwater, and improve water storage and use. Climate change is starting to be factored into a variety of development plans, such as how to manage the increasingly extreme disasters we are seeing and their associated risks, how to protect coastlines and deal with sea level encroachment, how to best manage land and forests, how to deal with and plan for reduced water availability, how to develop resilient crop varieties, and how to protect energy and public infrastructure. NASA, with its eyes on the Earth and wealth of knowledge on the Earth's climate system and its components, is one of the world's experts in climate science. NASA's purview is to provide the robust scientific data needed to understand climate change. I've already highlighted how data from the agency's GRACE and GRACE follow-on missions and ICESat-2 mission, as well as from radar instruments in space, has shown rapid changes in the Earth's great ice sheets. The JASON missions have documented an increasing sea level rise since 1992 using satellite altimetry. NASA makes detailed climate data freely available to the global community, the public, policy, and decision makers, and scientific and planning agencies around the world. It is not NASA's role to set climate policy or prescribe particular responses or solutions to climate change. NASA is one of 13 U.S. government agencies that form part of the U.S. Global Change Research Program, which has a legal mandate to help the nation and the world understand, assess, predict, and respond to global change. These U.S. partner agencies include the Department of Agriculture, the Environmental Protection Agency, and the Department of Energy, each of which has a different purview depending on their area of expertise. Started in 2010, NASA's Carbon Monitoring System, or CMS, is a forward-looking initiative established under the direction by the U.S. government. The Carbon Monitoring System is improving the monitoring of global carbon stocks, where carbon is stored around the planet, and fluxes, how carbon is cycled from one stock to the next. The ultimate goal is to make breakthroughs in quantifying, understanding, and predicting how worldwide carbon sources and sinks are changing, since this could have major ramifications for how our planet will respond to increasing emissions and/or efforts to combat climate change. The work will also help inform near-term policy development and planning. NASA's related Megacities Carbon Project is focused on the problem of accurately measuring and monitoring greenhouse gas emissions from the world's biggest cities. About 3/4 of fossil fuel carbon dioxide emissions come from about 2% of the land surface, the cities and the power plants that feed them. At present, the focus is on pilot projects in Los Angeles and Paris that sample the air there. The goal is to add other cities around the world and to ultimately deploy a worldwide urban carbon monitoring system that will enable local policymakers to fully account for the many sources and sinks of carbon and how they change over time. Although NASA's main focus is not on energy technology research and development, work is being done around the agency and with various partners and collaborators to find viable alternative sources of energy to power our needs. These sources of energy include the wind, waves, the sun, and biofuels. On May 24th, 2021, NASA and the White House announced a new set of emissions. On May 24th, 2021, NASA and the White House announced a new set of missions recommended by the Earth Science Decadal Survey more than 3 years ago, which will be developed under a program called the Earth System Observatory. NASA stated the Earth System Observatory will be a set of missions addressing the designated observables, a set of key observations that scientists recommended the agency pursue in the Earth Science Decadal Survey published in early 2018. NASA's new Earth System Observatory will design a new set of Earth-focused missions to provide key information to guide efforts related to climate change, disaster mitigation, fighting forest fires, and improving real-time agricultural processes. With the Earth System Observatory, each satellite will be uniquely designed to complement the others, working in tandem to create a three-dimensional, holistic view of Earth from bedrock to atmosphere. Areas of focus for the observatory include aerosols, cloud convection and precipitation, mass change, surface biology and geology, surface deformation and change. I'd now like to play you a short video describing how NASA's new Earth System Observatory will expand upon NASA's previous work, providing the world with an unprecedented understanding of our Earth's climate system, arming us with next-generation data critical to mitigating climate change and protecting our communities in the face of natural disasters.
As NASA prepares to send humans to the Moon and Mars, and peer even deeper into the universe, we turn with a renewed focus to our home planet of Earth. The next generation of Earth science begins with the new Earth System Observatory. The core of the observatory is an array of 5 new satellite missions that will study the atmosphere, the ground, and even what's happening underneath the surface.
These spacecraft will look at the Earth, each one of them their own way, and will integrate all the data in a common approach.
Taken together as a single observatory, we will have a complete 3-dimensional understanding of our Earth systems, how they work together, how one change can influence another. It will watch our planet change, driving solutions for better living, managing water and food resources, predicting natural hazards, coping with sea level rise in coastal communities, and heat islands in our cities.
Every 10 years, the best scientists in the United States and worldwide come together and create a strategy, the Decadal strategy. And it recommended that we build missions that together form an Earth System Observatory.
We're going to be looking at processes at the microphysical scale, at the large kind of convective scale, at the smaller scale in the oceans, and we're going to be investigating those, pulling that out, encapsulating that, putting that into weather models and climate models, and those are going to allow us to predict and project the future with far more confidence.
We can, from space, help farmers. We can help others that grow food around the Earth.
If there is an earthquake, we can get our models better, and from there we can predict better also in the future.
We can monitor fresh water both on the surface and underground to help water managers, both for communities as well as agriculture.
To build the observatory, we will expand our partnerships with commercial companies and international space agencies to take advantage of innovation and new technology.
We recognize, because of the global nature of the issues at hand, we want international partners to be part of that also. We're working together, and the science that we're doing has to serve all of us.
NISAR is our first major partnership with the Indian Space Agency in Earth science. It brings together 2 different kinds of radar systems that together will see changes in our Earth's surface that will help us predict natural hazards in the future.
The NISAR mission will measure changes in Earth's surface less than a centimeter across. It will measure the movement of glaciers and ice sheets, the dynamics of earthquakes and volcanoes, and changes in farmland.
We will observe the Earth every 12 days exactly at the right repeat pass orbit. We can study small changes in the Earth system sciences.
The Earth's climate is changing. We have documented the changes that we're seeing over the last few decades. We know that it's being driven by human activities, and it's absolutely essential that we continue to understand what's happening, what's changing, in order to better predict what's going to happen and perhaps help people make better choices.
Understanding how our planet and its climate are changing is the foundation for a more resilient and sustainable future. NASA's Earth System Observatory is the next step in this ongoing mission, a mission to the only planet we can call home.
Thank you very much for your attention throughout today's presentation. We will now transition to the question and answer session. Please enter your questions in the question and answer box. We will answer your questions in the order they were received. We will post the question and answer document to the training website following the conclusion of the webinar. Feel free to contact myself or my colleague, Amita Mekta, should you have any questions about today's presentation. You can also access the training webpage and RSET website in the links provided below. Thank you. So question number 1, can global warming cause extreme cold waves, for example, as we recently saw in America? And I believe they're referring to North America. And Alex, it looks like you would answer this one. Do you want to unmute and go ahead and answer?
Yeah, so thanks for the question. The main thing we wanted to say in reply to this question is that, of course, global warming can shift large-scale conditions, and these in turn can lead to extreme cold events. However, when we look at the grand scheme of observations, we see that the frequency and severity of cold waves are decreasing with global warming. And therefore, the human influence on cold waves in general is to decrease their frequency and severity. Some examples of what those large-scale conditions that could still lead to changing distributions in terms of cold waves would include things like changes in weather patterns, the role of sea ice in setting jet stream locations, for example, and ocean circulation in terms of delivering warm water to portions of Europe. All of these things could affect the cold extreme distributions and are therefore things that we're studying intently.
Alex, thank you so much. We're going to go on to question number 2. Can you please repeat what kind of aerosols have a warming versus a cooling effect? So to recap what was covered in the presentation, so aerosols, dust and smoke, both come from human as well as natural resources and have various effects on the climate. But sulfate aerosols, which result from burning coal, biomass, and volcanic eruptions, tend to cool the Earth, and other kinds of particles such as black carbon have a warming effect. So hopefully that helps to answer that person's question. Question number 3. Can this broadening of the land temperature anomaly, in this case, it was the animation shown in slide number 16, can it be also due to the disagreement among the CMIP models? And answer 3, I think, Alex, you might have answered. Do you want to go ahead?
Sorry, yes, for question 3, what's important to note here is that the distribution that was shown was based on observational records, not the CMIP models. And in that sense, this wouldn't be affected by observation or by model uncertainty. These are truly records of surface temperature.
Great, moving on, question number 4. If the solar irradiance is decreasing, and considering the negative radiative effect of continuously increasing aerosol concentration, how can we experience any dip in the increasing global air temperature curve during the upcoming few decades? If yes, then what may be its impact? Can it nullify the impact of global warming, that we are experiencing currently? Alex, over to you.
Yeah, so we can use our models and our observational systems to understand the signature of different parts of human emissions on the climate system. When we look in recent decades, we see both natural forcers and human forcers, as we described in this training here. The solar radiance has been decreasing in recent decades, while the aerosol concentrations come from human influences have somewhat countered the effects of greenhouse gases. However, we know that air pollution can have negative health effects, and therefore there is strong motivation even beyond climate change to reduce aerosol emissions and overall and lead to overall improvements in air quality. This, however, will have the effect of revealing more of that human influence via greenhouse gases. Therefore, we expect to see that greenhouse gas leading to that warming even more clearly in the decades to come.
Great, thank you, Alex. Question number 5. How does the seafloor accumulation of marine sediments reduce carbon from the atmosphere? And the answer being, at the ocean's surface, carbon dioxide from the atmosphere dissolves into the water, and phytoplankton in turn uses carbon dioxide for photosynthesis. Phytoplankton, again, are the base of the marine food web. So after animals eat the plants, they breathe out the carbon or they pass it up the food chain, but phytoplankton can also sink to the bottom of the ocean where they become buried in marine sediment. Over long timescales, this process has made the ocean floor the largest reservoir of carbon on the planet. And question number 6. Thank you for moving that. What should be the adequate carbon dioxide concentration? Alex, I believe you answered this. Please, over to you.
Yeah, so this is a very broad question here, and one that I would answer by saying that what we see from the science is that different greenhouse gas concentrations are associated with specific levels of global warming. And the kind of cumulative budget of how much carbon we emit leads to those global warming levels. Within each of those global warming levels, we see distributions of hazards and associated risks for human and natural systems. This therefore means that the policies we're setting in terms of target greenhouse gas emissions, concentrations, and global warming levels are really connecting many different motivations, and therefore the policymakers are weighing societal pathways against the resulting challenges for adaptation, mitigation, and risk management. The moral and ethical judgment entailed in setting an adequate CO2 concentration is therefore much beyond what a climate observation or model can show, and goes into deeper questions of ethics and socioeconomics and geopolitics. However, what we can show in the science is that every increment of greenhouse gases matters in terms of the overall climate challenge.
Great, thank you, Alex. Again, question number 7. Is the data collected by constellations such as Aura and Calypso available to the general public? And if so, how does one access it? So I'll preface this by saying that the United States American taxpayer pays for all these satellite missions that are launched, specifically through NASA, as well as other agencies such as NOAA. And so they don't want to charge again for the data sets for the missions that they've already charged the taxpayer to fund these missions. So once these satellites are up and collecting the data is freely available, not only to people in the United States, but anywhere on the planet. You can get access to the data, and we've provided the link below if you're interested in exploring specifically for Aura and Calypso. You can go to this link at Earth Data Search and you'll be able to access some of those data sets. So again, it is freely available, as are all of NASA data sets. So question number 8. Which of these data sets can be accessed in Google Earth Engine? So we have provided a link below that you can go and search for yourself on Google's website. And this is for the catalog that Google Earth Engine has collected from not only from NASA, but also from the European Space Agency and other space agencies. So we do, off the top of my head, I don't have a comprehensive list, but many of the missions and the associated data sets that are associated with them can be found on that catalog. So we do encourage you to go and explore there with the link provided. So question 9, is there a difference in the concentration of carbon over the daily range, night and day? So yes, there is. So during the day or in spring and summer, plants take up more carbon dioxide through photosynthesis, then they're released through respiration. And so concentrations of carbon dioxide in the air decrease. Then at night, or during the autumn and winter, which we're currently going into in the Northern Hemisphere, plants reduce or even stop photosynthesizing, which releases carbon dioxide back into the air. So there is a diurnal as well as a seasonal fluctuation in carbon dioxide. Question number 10. Has the Carbon Observatory mission, and I believe you're referring to OCO2 and OCO3, launched, and has data already been collected? And the answer is yes. Both the Orbiting Carbon Observatory 2 launched in July of 2014, and it's still collecting data since that time. And the Orbiting Carbon Observatory number 3 has actually launched and is now attached to the International Space Station and is also currently operational. ARCET is planning on having trainings on carbon monitoring in next year, actually. So we do hope that you will join us. So get on our listserv, learn about these trainings as they're coming up, because we will be having a training specific on this, and it will be dealing specifically with these satellite missions, OCO2 and OCO3. So do stay tuned for next year. Question number 11. Is El Nino responsible for global warming? Very good question. And are human beings responsible for El Nino? And another very good question. So El Nino is very complex and naturally occurring weather pattern. So it's natural that results when ocean temperatures in the Pacific Ocean near the equator vary from the norm. Humans are not responsible for El Nino. Normally, that is in years when El Nino does not occur, strong trade winds blow from the east to west across the Pacific Ocean around the equator. The winds push warm surface ocean water from South America west towards Asia and Australia, and cold water upwells from below in the east to take its place along the South America. And that's what gives South America fisheries such good fisheries, because that good cold upwelling that is occurring off that coast. But in an El Nino year, which again is a natural occurring weather pattern, the trade winds weaken or break down, and that warm water that is normally pushed west toward Australia and Indonesia piles up on the east side of the Pacific Ocean, extending from Chile all the way up to California. And this causes great changes in weather during the El Nino phenomenon. And specifically on the west coast of the Americas, it causes more precipitation and storms. So question number 12. How exactly is the temperature of the ocean rising? So data from the US National Oceanic and Atmospheric Administration, also known as NOAA, shows that the average global sea surface temperature, the temperature of the upper few meters of the ocean, has increased by approximately 0.13 degrees centigrade per decade over the past 100 years. So hopefully that helped to answer that. So question number 13. Where can we obtain local sea level rise data, especially for Southeast Asian countries? So if in the presentation, you remember we covered a lot of the tools from that data portal from the sea level rise. And so we provided that link below. And please, we do encourage you to explore that, because it does have, it has data portals for sea level rise, not only global, but also regionally. So you can explore for yourself how regional sea level rise can be impacting you specifically in Southeast Asian country, depending on what country you're interested in. So question number 14, which is the better NASA mission to provide a precise water level and volume in lakes? So current NASA missions that are contributing through either laser altimetry or radar altimetry, satellite altimetry are Jason 2 and 3, and we also have the ISAT-2 mission. All of these are currently operational, and they're providing surface height of lakes. And ARCET actually about a year ago held a training specifically on this, showing all the different current NASA satellite missions that are contributing to lake and reservoir height. So we provided that link for you below, and we do encourage you to go, if you're interested in this application, to explore that training to learn more. Question number 15. MODIS provides data for up to 20 years, but more than 30 years of data is required for climate change studies. Is 20 years of data sufficient for climate change studies? Another excellent question. So fortunately, we do have data extending back way before MODIS became operational in 1999, when the Terra satellite launched. So we have data from all over the world, from meteorological stations, from buoys out on the coasts and out in the oceans. We have from ships that are traversing all the seas and oceans, from planes for atmospheric temperature, and also from geostationary satellites that go back before the MODIS record. So they have all been able to give us a comprehensive view to contextualize the different temperature across the planet. So, but specific to MODIS, it has given us that 20 plus year data set, which has been crucial to help fill out really a global coverage of the planet. And we do have the VIIRS instrument, which is a continuity mission that's building off of that MODIS record. And fortunately, MODIS will continue for hopefully another few years. But it's a great question. 30 years is the optimum for trying to look at climate change studies. And sometimes, you might be limited depending on the geography of the planet. If you're looking only in the satellite era, but we do have, based on the other records, a very good idea in terms of how the temperature's been changing, both on overland and over the ocean. So we can do these assessments with the data sets that we have. Question 16. About the regional sea level change, what are the main reasons why the Earth doesn't behave like a bathtub? For example, sea level rise on the opposite side of where ice, glaciers, melts. Thanks. And I think we did cover this in the presentation, but the ice sheets over Greenland and Antarctica are immense, and they do exert enough gravitational pull to draw a substantial amount of ocean water toward them. But as these great ice sheets are losing mass, especially Greenland, but also Antarctica, so we see something quite bizarre happen nearby. So sea level rise will actually fall in an area stretching more than 1,000 miles from the ice sheet. And that has to do with the difference in gravitational pull as that ice is lost to the sea and spread out into to lower latitudes. So another factor that can also affect that sea level so it doesn't behave like a bathtub is that a sea level also can shift due to wind patterns, which are carried by ocean circulation and ocean currents. So that all has to do with the variability within different sea levels. And also the complexities do not stop there. As water is added to ocean basins, the basins themselves adjust to the extra weight. And so they can become more like a kid's pool in terms of like flexible plasticity. And ocean floor can actually sink. And the deformation is slow, but it changes the distribution of ocean water over time. So there's actually a number of reasons why ocean surface height does not stay uniform like a bathtub. And we do hope that you will explore more on your own. And so question 17, I think, Alex, you would be a perfect person to answer this. How is NASA connected to the IPCC, IPBES, UNFCCC, UNEP, and other international policy think tanks on climate change and impact on society? Alex, over to you.
I'll keep this a short answer, but what you see on the screen, we actually have NASA scientists participating in a lot of these international efforts to assess climate change information and its effects on things that we care about, including the biosphere and development. So I was actually one of the coordinating lead authors for the IPCC 6th Assessment Report, Working Group 1. And you can see a little bit more about some of the things we did in part 2 of this training. We also have NASA scientists, of course, contributing data and acting as expert reviewers for these various assessment reports. And that together helps make sure that the cutting edge climate information that NASA provides and the expertise of its scientists are making it into these reports.
Wonderful, thank you, Alex. Question 18, could you mention some examples of successful measures for mitigation and adaptation to climate change around the world? Alex, over to you.
Yeah, so there's a long list of these, and it's very exciting, I think, because the current set of research and decision-making is very much starting to focus on the fit-for-purpose mitigation and adaptation efforts and tailoring it to the local decision context and other things. Just some quick examples, of course, mitigation includes any effort to reduce greenhouse gas emissions or sequester carbon. And that would entail things like reducing overall energy demand, shifting from one fuel type to another with a lower greenhouse gas emission footprint, or protecting natural resources like tropical forests. Within adaptation, of course, there are big differences across regions and across impact sectors and even within a given sector like agriculture. But some examples there would include things like reducing vulnerability by building seawalls or selecting heat-tolerant seeds for crops, but also things like reducing your exposure. So how much is in the path of where there could be wildfire. And then there's also effort to pool risk, which allows us to better manage the risks associated with those climate change, for example, through things like flood insurance.
Great, wonderful. And question 19, how are the spaceborne climate data sets validated? Look, somebody answered this. In most cases, with ground-based and/or aircraft-based measurements. So as these satellites fly over a given part of the planet, there are scientists out there collecting data in the field during the time of the satellite overpass, or within 1 hour, give or take, and they're able to calibrate a lot of the instruments. And this takes place over many months before the satellite, the data products are provided to the public. So they're highly calibrated and validated before these data sets are shared with the public. So this is one of the main ways that NASA scientists and other scientists from other agencies are able to do this. So question 20, what type of analysis is performed in studying the effects of sea level rise to coastal vegetations such as mangroves or seagrass? Alex, over to you.
Yeah, so scientists use a combination of models and observations and specifically designed experiments to understand how climate change and sea level rise affects ecosystems like these coastal vegetation systems mentioned in the question. That helps us to specifically understand the biophysical effects on the crops themselves, the ecology of the vegetation environment, and the ecosystems that depend on those resources.
Wonderful. Alex, thank you so much. And then let's see, question 21. I think most of the Earth observing data sets have a spatial resolution of 5 kilometers to 20 kilometers. Do you think that variability and magnitude of various meteorological variables in EO data sets is correctly quantified in mountainous regions, such as in South Asia, as compared to hilly areas and flat lands? Alex?
So Earth observation data sets can span a huge number of scales, even much lower than this 5 kilometer, down to the meters scale, for example, in some situations. So we are increasingly capturing this fine scale resolution. But what I wanted to reply here is to recognize that there's an array of methodological approaches that we use to address these scale challenges. These include using dynamical and empirical downscaling models, as well as bias adjustment to shift and fill in gaps to impose and understand finer resolution features within these coarser climate data sets. When we do this, we also have to recognize that the process of this downscaling and adjusting that scale can shift some of the statistics and the expectations of how data should be used. For example, we would expect to see a heavy precipitation event when averaged over a large area would appear lower than the heaviest downpour you might find within that. So understanding kind of the indicative nature of what the climate data sets are showing is quite helpful.
Great, Alex, thank you again. Question number 22. So what service is most used to observe pluvial flooding? Are there known and agreed upon standards? Alex?
Yeah, so this is something that was mentioned in the training here, where we have great new advances with the Global Precipitation Measurement Mission. And one thing to highlight is the iMerge product. This helps us observe heavy precipitation events. But of course, to understand pluvial flooding, we also have to understand the environment in which the rain is falling. That means we have to understand things like the engineered tolerance levels of local stormwater drainage systems. So this is one of the reasons we work both from our observational standpoint, but also with stakeholders to understand what are those critical thresholds at which flooding is likely to occur, and which resources and assets are potentially in danger when that does happen.
Wonderful. Question 23. A lot of countries are in a race to develop. It is clear that more developed countries mean more emissions. How is NASA taking into account this social variable for the forecasting or estimation of the impact of it in the climate change? Alex?
So this will be covered in part 2. When we run our climate models out into the future, we use a set of scenarios that reflect various choices in socioeconomic development and the associated emissions that come from different regions of the world in light of those socioeconomic choices and broader policy choices. These things reflect things like different levels of technological advancements, fossil fuel usage, and international cooperation. By using these scenarios, which are effectively, what would happen if these choices are made, it gives us an ability to explore the ramifications of these policy choices and identify which of these pathways allows us to meet the broader targets, both of sustainable development goals, broader climate change targets, and the socioeconomic advancements that we hope to achieve.
Wonderful. And question 24, what are the new instruments that were added on Landsat 9 related to climate change? So to answer this one, the instruments that just launched 2 days ago, actually, on Landsat 9 are going to be pretty much the identical instruments that are currently operational on Landsat 8. That is the Operational Land Imager, OLI, as well as TIRS, the Thermal Infrared Scanner. And it's actually OLI2 and TIRS2. And how these will contribute to climate change is we see a lot of the effects of climate change played out in terms of the land processes, in terms of maybe it's shrinking mangroves, maybe if it's shrinking wetlands, et cetera. And so Landsat is able to observe this, and the records have gone back pretty much 50 years at this point. And so it's going to contribute to the land change that we observe over land. And that TIRS2 instrument is going to be crucial to observing land surface temperature, because it collects data in the infrared, long wave infrared, which can be used to observe, say, like urban heat islands in different parts of the planet. And so it's really crucial to observing how places are heating up, and also has a very high, in terms of surface temperature, land surface temperature, it has quite a high spatial resolution. I believe it's 90 meters. So it's really effective at monitoring changes in land surface temperature. So again, this is a continuity mission, and the instruments are basically the same that are on Landsat 8. So great question. Question 25, in the graph on slide 36, is it known what happened between about 1935 and 1945 to raise the carbon dioxide and the global temperature? This time frame makes me wonder if that was an effect of World War II. Alex?
Yeah, so that's an astute observation there. There is a connection between the time period around World War II and climate that is noted with things like high aerosol concentrations. There are many other things that go into this, so I don't want to oversimplify it in that way, but it is a noted effect. There were other things happening in the period just prior, such as the US Dust Bowl, which is noteworthy for land use and land degradation changes that caused particular regional extremes. So these are the types of things we can use our model to disentangle. And you'll see in part 2 that when we separate the natural and the human-induced causes, we can start to explain some of these things.
Alex, thank you so much. And that concludes it. We want to thank everybody that joined today. Really, the questions, we really appreciate it. They're great to kind of gauge some of the things that you're thinking about in terms of your own planning, in terms of your own research. Thank you to everybody that joined us. I know this has been quite a long session today. We do hope you'll join us 1 week from today to listen to the presentation for part 2, which will delve more into climate modeling. That's actually going to be presented by Alex, who's been answering a lot of the questions today. So before we end, I want to give a huge thanks to Alex Ruane for participating in this training, for helping answer the questions. Also, Dan Bader, also from Goddard Institute for Space Studies. I also want to thank my colleagues, Amita Mekta, who's been crucial to this training success, as well as my colleagues, Brock Blevins, Selwyn Hudson-Odoi, and Jonathan O'Brien. They've all been behind the scenes, making sure everything's been running smoothly. So big thanks to the whole RSET team, and thank you to everybody that joined today. We hope you got a lot from this, and do stay tuned. We hope to see you all in 1 week for part 2 of the climate training. So have a wonderful day, and we hope to see you in a week. Thank you.